The group of 15 elements include nitrogen, phosphorus, arsenic, antimony, and bismuth. Although we have abundant phosphorus on Earth, but phosphorus is actually widely distributed. Enriched ores are rare. There are generally 5 valence electrons for each element. The covalent radius increases with the atomic number. Only the anionic radii of nitrogen and bismuth are available. Only bismuth has metallic radius of 182 picometers. The electronegativity values of nitrogen is the highest. Others have similar electronegativities. Group of 15 elements mainly form covalent bonding. Single bond, double bond, even triple bond. The typical covalent bond enthalpies are given on the slide. N single bond is relatively weak, so is the OO-FF bonds. It's believed that repulsion between lone pairs on adjacent atoms is responsible. See the graph on the right here. Similarly, NO and Cl and NF are all weak due to the repulsion from lone pairs. Single bonding of nitrogen with an atom without lone pair electrons is strong, for example, ammonia. Ionization energies increase rather sharply after the removal of p electrons. There is a slight difference of IE values between phosphorus and arsenic. Nitrogen, single atom, reacts with many metals. Dinitrogen is chemically inert to some extent, but it reacts with lithium, aluminum, silicon, germanium, and many deep lock metals under heating, forms coordinated complexes with the deep lock metals. Phosphorus has as many as 12 allotropes, either crystalline or amorphous. 3 of the 12 are well known: white, red, and black phosphorus. Each group of 50 elements forms a trihydride: ammonia, phosphine, arsine, and others. Other hydrides of nitrogen include hydrazine, hydrogen azide. Hydrogen azide is a colorless liquid prepared by reaction of sodium azide and acid. In the laboratory, we have to handle azides very carefully because it's explosive. Nitride is a compound of nitrogen, has a formal oxidation state of -3. The nitride ion, N3-, does not exist because it's so basic that it would be protonated to form ammonia and hydroxide ion. Nitrides include saline nitrides from group 1 and 2 metals and aluminum. The saline nitride is water-sensitive, covalently bonded nitrides bonding with the p-block elements, interstitial nitrides of d-block metals, and per-nitrides from the combination with the group 2 metals. Alkali metals can form phosphides containing groups of phosphorus atoms forming chains or cages. Gallium arsenide, an important 3,5 semiconductor. Highly pure gallium arsenide is prepared by CVD method, chemical vapor deposition. Other important 3,5 semiconductors comprise aluminum arsenide, gallium phosphide, and others. Important nitrogen halides are trihalides, tetrafluoride. Nitrogen tetrafluoride is the most stable of the trihalides of nitrogen. It's a colorless gas, resistant to attack by acids and bases, but is decomposed by sparking with hydrogen, for example. Tetrafluoride may lose its fluoride ions to strong acceptor. For example, arsenic pentafluoride forms a salt, and all the oxofluorides and oxchlorides of nitrogen are unstable gases or volatile liquid, which are rapidly hydrolyzed. Phosphorus forms the trihalides and pentahalides, but phosphorus pentaiodide is unknown until now. The halides are all hydrolyzed by water. See the equation, for example. Although trifluoride reacts slowly, arsenic and antimony also form the trihalides and the pentahalides. The trihalides of bismuth are all well characterized, a kind of Lewis acid, but bismuth pentafluoride is the only pentahalide known. It's interesting that enthalpies of formation of the oxide from nitrogen are all positive, suggests that oxides are thermodynamically unstable. In fact, for example, nitrous oxide is quite stable at room temperature because the activation energy of its decomposition is as high as about 250 kilojoules per mole. Nitrogen monoxide and nitrogen dioxide are paramagnetic, while all others are not, indicates the existence of unpaired electrons in nitrogen monoxide and nitrogen dioxide. The reaction of nitrogen dioxide with water gives it a 1-to-1 mixture of nitrous and nitric acids, so the atmospheric nitrogen dioxide is corrosive and contributes to acid rain. Nitrogen tetroxide reacts with the concentrated sulfuric acid, gives the nitrosyl and nitrocations. Nitrocation, nitrogen dioxide, and nitroanion have the same number of atoms, similar geometric structure, but a different electronic structure. Oxoacids of nitrogen include hyponitrous acid, nitrous acid, nitric acid, and its derivatives. Hyponitrous acid, nitrous acid are weak acid. Nitric acid is a colorless liquid, but must be stored below 273 Kelvin to prevent slight decomposition, which gives the acid a yellow color. Most metal nitrates decompose, release oxygen. See examples shown here. Each of the group 15 elements from phosphorus to bismuth forms two oxides, trioxide and pentoxide. Generally, pentoxide are acidic. Phosphorus trioxide is acidic. Arsenic and antimony trioxide are amphoteric. Bismuth trioxide is basic. Each phosphorus atom in phosphorus trioxide carry a lone pair of electrons, and phosphorus trioxide can act as a Lewis base. Oxoacids of phosphorus include phosphinic acid, phosphonic acid, phosphoric acid, hypodiphosphoric acid, diphosphoric acid, triphosphoric acid. The basicity of each acid does not equal the total number of the hydrogen atom for some oxoacids. For example, phosphonic acid and phosphinic acid are dibasic and monobasic, respectively.